So when we're trying to do a problem like this, we are trying to think about how we can either multiply or divide to the number in the logarithm using the numbers we're given. So for the natural log, we only have natural log of 2, natural log of 3. So we're trying to think of how do you multiply to 18 using 2s and 3s. Well, you can take a couple steps or one step. I'm going to write this as the natural log of 9 times 2. And then I'm going to write that as the natural log of 3 times 3 times 2. And then I can say that's the natural log of 3 plus the natural log of 3 plus the natural log of 3. And I feel like this step especially was this, natural log of 3 plus natural log of 3 plus natural log of 2. Excuse me. I feel like this step especially was a step where people kind of struggled. A lot of people maybe multiply these together instead of adding them together. So I would really encourage everybody to look at your graded homework and see what you might have missed, what you might need some help with. Also, even problems that you might have gotten full credit on, sometimes there still might be something that was a little bit off. So I really, really encourage everyone after I've graded in general, right? Not just for this assignment, but for most assignments, all assignments, quizzes also, but all assignments, tests, whatever. I think it really is worthwhile to look at your homework that's been graded and to see what you might have missed and to kind of get help with that if you feel like you need help. So here, I'm going to write this as the natural log of 3, which is 1, 0. That's right, this is approximately, let me let Sandra in here. There we go. So this is approximately 1.10 plus 1.10 plus 0.69, which is going to be, let's see, 1.1 plus 1.1 is 2.2, plus 0.69 is 2.89. And then for this one, we're only given log of 3 equals 0.48. So there's clearly something tricky going on. By the way, I also want to point out, right, log and natural log, two different things, right? This is log base 10. This is log base E. So for log, well, let's see. I see that log of 270 is log of 27 times 10. Now, here's the thing about log. It's log. That's a very old, I guess it's kind of an old reference. Anyway, not important. When you have a log base 10, if you see a 10 in there, you want to keep that as is. You don't want to break up 10 into 2 times 5, even though you could. I can rewrite this as log of 27 plus log of 10. And log of 10 is just 1. Because you're saying 10, which isn't written there, to what power equals 10? Oh, it's 1. So this, instead of writing it as 3 times 3 times 3, I'm going to write it as 3 to the third. Log of 10 is 1. And then 3 times, then I can use the exponent rule. It says that if you have log of something to a power, you can bring that power down in front. So this is 3 times log of 3 plus 1. And then that's approximately equal to 3 times log of 3, but log of 3 is approximately 0.48 plus 1. And then 3 times 0.48 is about 1.46, I think. That's not right. 1.44, that's right. 1.44 plus 1, which is 2.44. So that's how I would do these two problems. A couple other things I saw that I wanted to just make note of. There was this problem, I forget, I think it was log of 10 times the square root of 10. And a lot of people kind of made this 10 the base down there. It's not. It's something you're taking the log of. It is also true that the base is 10. And if we want, we can just rewrite this as log base 10 of 10 times the square root of 10. And then there's like 3 or 4 ways you can do this. I would probably, I'm going to show 2 different ways. One way would be to break it up. Say log base 10 of 10 plus log base 10 of the square root of 10. Log base 10 of 10 is 1. Now, log base 10 of the square root of 10 is log base 10 of 10 to the, so be careful, 10 to the 1/2 power. And I also want to talk about this. The 1/2 power is just the 1/2 power. It's not equal to the negative second power. A lot of people are kind of getting this confused with being a negative because right, when you have a negative power, it becomes reciprocal. So I want to point out 10 to the negative second is 1 over 10 squared. 10 to the 1/2, there's nothing else you can really do. It doesn't really change. It's just 10 to the 1/2. But what I can do is I can say, oh, this 1/2 power is going to come down in front. Let's say this is 1 plus 1/2 times log base 10 over 10. And then log base 10 of 10 is 1. So this is 1 plus 1/2, which is 3/2, or 1.5, either way. And then the last thing I wanted to address that I saw, just because I saw a few things that were interesting to me. And this last one I think was really interesting and not wrong, just very different. So there was one homework problem that it was kind of like, I don't remember exactly what it was. I'm going to make this one up. It was like log base, I don't know, 49 of x equal to 1 over 7. Is that right? That's not right. Sorry. Let me think for 1 second. It was, I could actually look it up, I suppose. It was, sure. I think it was something like that. Let's go with that. So there's, again, with logarithms, there's lots of ways to solve things. Typically, and now I'm going to show you what I would do, and then I'm going to show you what other people do, which is also neat. I just want to point out that there are sometimes easier ways to go. So this one, if I'm trying to solve for x here, I would most likely be, oh no, I remember what it was. It was slightly different, sorry. It was this. Apologies, sorry. It was log base x of, sure, something like 49 equal to negative 2. Sure, yeah, that was more like the problem. And so I would solve this by writing x to the negative 2 equal to 49. And then there's a number of ways you can do this, but the easiest way, if you have x to a power and you want to isolate x, the easiest way to get x by itself is just to raise both sides to the same power that's the reciprocal of this power. So I can say, oh, that means x to the negative second to the negative 1/2 equals 49 to the negative 1/2. Power to a power, we multiply the powers and get x. What's a negative power do? It makes the whole thing a reciprocal. So this isn't equal to negative 2, but it is equal to 1 over 49 to the positive 1/2 power. The 49 to the 1/2 power is the same as the square root of 49, which is 1 over 7. So that would be one way. This would be the way that I would think is the easiest way to do it. That doesn't mean you have to do it this way. I just want to point out that this seems, at least to my mind, very kind of logical, where you're trying to do as little work as possible. However, I just want to point out that there are certainly other ways to do this. One thing I saw, which I thought was kind of interesting, was people doing this. They immediately went and said, oh, well, I can rewrite this as log base 49 of x equals the reciprocal of that. Which is kind of funky. It is true, but it's kind of, there's a lot of math in there that is not being said, which again is okay. And then you can rewrite this as 49 to the negative 1/2 equals x, which gets us exactly to the same place we're over here. So this is okay. I just want to point out that there's kind of a lot involved with that. What you're actually doing here, or at least what Alyssa doing, is we're actually using the change of base formula, which I know we haven't talked about in this class, but the change of base formula says if you've got a logarithm, you can change the base to any base you want with the formula. So if I have log base 49 of x, I can rewrite this as pick any base you want. I'm going to pick base b. This is log base b of x divided by log base b of 49. Where b can be any base you want. And then the base we're using here is base, sorry, where'd you go? Yeah. Oh, sorry, we were starting with this, not with that. That's okay. Let me rewind. And then we'll get to class I. So I've got log base x of 49, and I can write that as log base b of 49 over log base b of x. So if you're using the change of base formula, it's always whatever base you want. The argument goes in the numerator log, and the base goes in the denominator log. And then here, if you're trying to get to this, the base you're actually using is base 49. So this is log base 49 of 49 over log base 49 of x. So that's equal to, well, log base 49 of 49 is just 1. And so what we're saying here is this is equal to -2. And then we're taking the reciprocal of both sides to say that log base 49 of x is equal to the reciprocal of -2, which is -1/2. So for those of you that did something like this, I just want you to be aware of kind of what's really involved with all of that. It's okay to have done this, but just know that there's kind of a lot there. I would encourage everyone to, when you're trying to solve a logarithmic equation, one of the things that's really worth doing right from the get-go is to rewrite it as an exponential equation. And I thought I heard someone starting to say something, but maybe I'm just hearing my wife and imagining things.
Oh no, it was me. I had a question.
Okay.
It was for warm-up question number 1.
Sure.
My process was different just because when I seen 18, I immediately thought of 6 times 3. So I ended up splitting that into natural log of 3 plus natural log of 6. And I used my calculator to determine what the decimal would be for natural log of 6. But I wanted to ask, would you recommend we use that method or use the logs that are given to us?
So I would say that for these problems in particular, the idea here was to not use a calculator. So you're certainly not wrong to break it up as natural log of 3 plus natural log of 6, but we then have to just go one step further. So we can say that this is the natural log of 3 plus the natural log of 6. And then instead of using a calculator for natural log of 6, we can say, oh, well, 6 is 2 times 3. So we can break that up as the natural log of 3 still, right? We've got this natural log of 3 here, plus this, which is going to be the natural log of 2 plus the natural log of 3. What I should really say is it's fine to factor it any way you want, right? I said 9 times 2, you said 6 times 3. But if we factor it as much as possible down to like the prime factors, we're both going to get to the same place where it's going to be 3 times 3 times 2, right? 3 times 3 times 2. So I would say for this type of problem where they're giving you the decimal approximations, the intention is not to just say, oh, well, natural log of 6 with the calculator is whatever it is. The intention is to get it into these kinds of expressions so we can then just use what we're given.
Okay, thank you so much.
You're welcome. Thank you for the question. Okay. As usual, if there are questions about the homework that you have, don't hesitate to let me know, either via email, come to office hours, all that kind of jazz. So I think we've actually kind of caught back up to where we wanted to be schedule-wise, which it wasn't exactly my intention, but it's certainly not a bad thing. So we're looking at class I today, and if you have looked at the schedule, which not that you should, but if you have looked, you will notice that class I is actually spread out over 2 days. So we're gonna give ourselves 2 days for this, and maybe depending on how much time we spend on this tomorrow, if there are other things we want to review tomorrow, we can certainly do that as well. But let's go ahead and talk about class I, which is exponential growth and decay. I kind of have the hiccups like all kind of morning. I'll try not to be grossly hiccuping / burping because sometimes that happens. Yeah, we will try to not be super gross. And by we, I mean myself, because you guys are not gross. I mean, maybe you are. I don't know what you're doing. You're unmuted. That's fine. do whatever you want. Also, happy January 21st. A great day. So, exponential growth occurs when a population grows at a rate proportional to its current size. So, we can say, for example, a population might grow 4% each year. That's an example of exponential growth because you're not growing by the same amount of people each year. Right? If you start with 1,000 or a million, let's say a million. Start with 1,000,000 people. The next year you're going to have 1,000,000 people plus 4%, and then the next year you're going to have 1,000,000 people plus 4% of that plus another 4%. So you're getting this kind of cumulative growth, this kind of compounding of growth, just like compound interest. In fact, this is why we talked about compound interest before this. One of the reasons is because they very much leads into it. So, yeah. But the important thing here is that the rate of growth of a population, but it can be really kind of, there are lots of things that grow or decay exponentially. The rate of growth of your population, for example, is proportional to the population size. This is actually a very important aspect of this. So next quarter, for probably most of you, or either in 16A, 17A, or 16B, 17B, you will definitely see this idea come back again, but it'll have all the language of derivatives involved with it. So when we say something like this, when we say a rate of growth is proportional to the population size, what we're really saying is the rate of change, also known as the derivative, which I know we haven't talked about, we won't talk about in this class, we won't define this class, but the idea here is that the rate of change, the derivative, is some constant multiple of the population or the function. So that's kind of the idea. That's the differential equation that is describing the situation. Now, we're not going to talk about the differential equation itself. We're going to talk about the solution to it. But here are some things other than population. So we can have human population. I mean, and there are lots of things, right? Humans, populations kind of grow exponentially depending on the environmental factors. You could have bacteria are often the example we go to because they do grow exponentially until you, at least in the beginning. You can have radioactive substances. We can talk about animal populations. We can talk about atmospheric pressure. That's one that I will never really talk about, but definitely comes up in 17A for sure. There are lots of things that grow exponentially or decay exponentially as things change. Atmospheric pressure as elevation changes, I should say. Typically, except for this last example, we're usually talking about how one thing is changing as time is going forward. Atmospheric pressure is kind of an exception to that example, right? Atmospheric pressure is talking about how the pressure is changing as the elevation is changing. But you're always talking about how one thing is changing as another thing is changing. So here's the model for exponential growth or decay. Model just being a fancy word for the function. So we can model it as y of t is equal to c times e to the k times t. And do I want to say stuff? Yeah, I do. So here's how I usually read this. Y of t is the population, or more generally, the amount of stuff at time t. So this is the, right, just like with our, there's a word I'm looking for, just like with our compound interest formula, right? The left-hand side is the amount of money we have time t. I guess I could also say, right, this would also be true for continuously compounded interest. Right? When you continuously compound interest, your money grows exponentially. Right? This is literally the same formula, just using different letters. Right? Our formula was A equals P e to the RT. I just wrote C instead of P K instead of R, and Y instead of A. Same formula. So Y of T is the amount of stuff we have at time T. Stuff being money, bacteria, radioactive material, people. C, the constant here, is the initial amount of stuff. T is, of course, the amount of time. And K is the growth rate. I'm not going to write what T is. We know that T is time. But K is the growth rate. So for interest, right, for the continuously compounded interest, the K value was the R value, which was the interest rate, or the rate that the money was growing at. For other things, it's the same sort of idea, but it's, yeah, we call it the growth rate. Let's look at some examples here. Okay, so what do I got here? For example, consider a medical researcher. Or use a little bit of typing there. Consider a medical. Sorry, it's getting a lot of use. A medical researcher studying a newly discovered bacteria. At time 0, we start with 100 bacteria cells. Its growth, meaning the number of cells at time t, is modeled by the following equation. Y of t equal to 100 e to the 0.25 times t. So we can kind of look at what this looks like. Sorry. And so, I should say one more thing, where time is measured in hours. So we could ask lots of questions like how many bacteria are going to be in 1 hour or 2 hours or 3 hours or 4 hours. Well, as I pointed out, the growth is going to be exponential. We can make a list, sure. Let's make we never make tables like this, but I guess we could since this is the space I've got. So let's say the time and the amount of bacteria. So after, it's 0 hours. If I plug in 0, 0.25 times 0 is 0, e to the 0 is 1, 100 times 1 is 100. If time is 1 hour, well, I'm going to get 100 times e to the 0.25 times 1, which is a 0.25. And e to the 0.25 is approximately 1.28, and 100 times 1.28 is approximately 128. Let's look at 2. So we're going to kind of do some of the math on it, right? 0.25 times 2 is 0.5. So we're going to get 100 times e to the 0.5. I'm not doing this next part in my head. I've just written it down already. That's going to be approximately 165. Let's do one more, and then we'll do one more. So if I plug in 3, I get 100 times e to the 0.75. And that's going to be approximately, what have I got here? 212. So what I want to point out, because this is kind of a key thing, is that the amount we're increasing the time interval by the same amount each time. That's terrible. So right, 1 hour, 1 hour, 1 hour. Between the 0th hour and the 1st hour, the population increased by 28 cells, or the number of bacteria increased by 28 cells. So right, so we added 28. But then from the first hour to the second hour, the population increased by, let's see, 37 cells. And then from here to here, the population increased by, I don't know, 47 cells, I think that number is, yeah. So the point I want to make here is that even though the time intervals are the same amount each time, since we're growing exponentially, you're always going to be increasing the number of cells that we grow by for the same time interval. That's kind of one of the hallmarks of exponential growth, is that your rate of growth is increasing because it's proportional to the population size, and the population size is increasing. And just to back up, right, that idea should be not too terrible, right? I always like to say, like, if there are more humans will make more humans, right? So if we start off with 1,000 people, we're going to be making not a lot of people, but as the population grows, we make more people because that's what we do. And then if we plugged in 24, we get some number like 100 times e to the 24 times 0.25 is 6. 100 times e to the 6 is a large number. It's 40,430. That, what was the word I was looking for? That got out of hand. There's actually a word. That escalated quickly is what I was trying to say. I've been not finding the words I want to find all the time lately, which is unfortunate, but oh well. So, right, after an hour, it's 128, after 2 hours, 165, after 3 hours, 212, and then from 3 hours to 24 hours, we get to 40,000. So there's a lot, right? Things are getting bigger much faster. Here's what the graph of this particular example. Why would I graph it for you by hand when I can graph it for you using a computer? Not that you shouldn't graph by hand. I don't mean graph by hand. So the idea here is, right, that this is time. This is the amount of stuff at time t. Right, we're starting off at 100. And in the beginning, right, the rate of growth, right, we're not really increasing that fast, but it really kind of starts to just go up and up and up. It still does, right? It doesn't ever go completely vertical. Although if you graph it on like a graphing calculator or a computer, it's going to look kind of vertical just because it gets super duper steep, but it's never actually vertical because you can always make the amount of time larger. So right here we have kind of slow growth. Here we have more rapid growth. So exponential growth or decay, as we'll see, typically follows this pattern of starting off slow and then getting bigger much faster as time goes on. So I will also point out that solving these types of problems that we're going to do today and tomorrow is very, very similar to what we were doing with the compound interest problems, where we're given an amount of stuff or an amount of stuff later or a time, or we're kind of asked to find the thing that we didn't know. Or I won't say an interest rate, but a rate of growth. So, right, typically we're going to have this sort of equation, y equals c e to the kt. I know I just erased it. Did I just erase it? I did, yeah. It's all right. Where, right, this is the amount of stuff we have at time t, it's the amount of stuff we're starting with, k is the growth rate, t is time. And we're going to be usually given like 3 of those things, right? There are 1, 2, 3, 4 different things to plug in for. We're going to often know 3 of them and have to find the 4th one. That is often how these problems work out. Kind of used my board space poorly here. Let's go to the other. I can just erase here. We don't need this. So let's look at some actual examples of problems. Excuse me, like the following. A colony of bacteria. This over here is growing exponentially. In a petri dish, sure. Initially, so when I use the words initially or at the beginning or whatever, that means when t equals 0, right? At time equals 0, at the beginning, we have some amount. There are 40 bacteria. And then 2 hours later, there are a million. No, not million. 2 hours later, there are 120. And we'll ask a few questions. So typically, even if it's not asked, the question you should always probably answer for a situation like exponential growth or decay is, what is the model? We are going to ask it. So what is the model for this situation? I would say, what is the model for the growth of the bacteria? Well, you might be like, well, James, that's a dumb question. The model's right there. Yes, I know that's the model. What I mean by this question is specifically, what are the values of C and K that make this model this model? Okay, well, here's the way I usually like to do this. I find it easiest if I make a table with my T values and my Y of T values, or the time values and the amount values. I know time equals 0. The amount of bacteria is 40. And I know that 2 hours later, so when time equals 2. So implied here is that we're measuring time in hours. We're always measuring time in the units given. And then 2 hours later, the amount of bacteria is 120. And we didn't say 120 more, we said 120 total. This helps me put things into this formula correctly. So I'm going to insert first, usually if you've got when t equals 0, that's what you want to start with. So I'm going to plug in 0 for t and 40 for y. So 40 equals c times e to the k times 0. I don't know what k is yet, but I'm about to solve for c because c times e to the, well, k times 0 is 0. And what's e to the 0? Everybody, what's e to the 0? Anybody, what's e to the 0?
Would it be 1?
It would definitely be 1, yes. Anything to the 0 with 1. With one exception, 0 to the 0 is undefined. So yeah, anything to the 0 is equal to 1, except for 0 to the 0. Yeah, so e to the 0 is 1, so c times 1 is c. So this means that 40 is equal to c. This shouldn't surprise us because we said before that the value there, that c, that's the amount that you start with, or the initial value. You could also think of it as the amount of stuff at time 0. So if you know how much there is at time 0, you can just say, oh, I know that my c is going to be that number. What I'm really trying to say with all these words is you don't have to go through this work to figure out c. If you know how much you have at time 0, you can just be like, bam, I know c, it's 40. But then we're going to use the other piece of information. So we use that to get that. And then we're going to use this to say, well, now I know that y equals 40 e to the kt, but I still need to find k. And really, this is always our job for these kinds of problems. If we don't know c and or k, typically before we can do anything else, we want to find them. So now I'm going to plug in time equals 2 and the amount y equals 120. And I'm going to get 120 for y equals 40 e to the k times 2. Now we're trying to solve for k, which is in the exponent, which is going to mean we're going to have to use a logarithm. This is usually true. If we're trying to solve for something that's in the exponent, we usually have to use a log. Before we can use a logarithm, though, we need our base without any coefficient here, right? And this is not 40 e to the k times 2. This is 40 times e to the k times 2. That 40 is jamming up the work. So let's divide both sides by 40. So 120 divided by 40 equals 40 e to the, usually people rewrite this as 2k just because it's typical to write actual numbers in front of constants or variable numbers. The whole reason we divided by 40 was to make this 40 cancel out. And then 120 divided by 40 is 3. So 3 equals e to the 2k. And then we take the natural log of both sides. It's almost always going to be the natural log because it's almost always going to be a base of e over here. So the natural log of 3 equals the natural log of e to the 2k. What's the natural log of e to the 2k? It's just 2k, because the natural log of e is just 1. So we don't really cancel this out, even though I know people really want to. What we really should do is at least bring the 2k down first. So you can just say it's 2k, that's also fine. But I would probably show the work of saying that the natural log of 3 equals 2k times the natural log of e. But then the natural log of e is just 1. So then 2k equals natural log of 3. And if I can fit this in here, then the natural log of 3 divided by 2 is equal to k. Which hopefully you guys can kind of read that. So again, this says k equals natural log of 3 over 2. So to answer the question, what's the model? Well, the model is this with our actual values plugged in. So our model for this particular problem is y, or y of t, you can write it either way, is equal to c e to the k times t, where c is 40 and k is the natural log of 3 over 2. I often like to put this in brackets, just so that I know that, oh yeah, it's all of this as the exponent of e. So there's our model. Great. Now we can
I ask a question real quick?
Go right ahead, yes.
Do we want to plug ln of 3 over 2 into a calculator?
No, not generally.
Oh, okay.
Fair question, though. Typically, we leave our k value as the thing there. Now, yeah, man, I'm kind of torn about this next part. Yeah, I should say this. So the next thing I'd say applies more if you're going to the 17 series. I feel like the thing we do. So I just want to show you something. So here's our equation. Y equals 40 e to the natural log of 3 over 2 times t. No, I'm going to wait. We'll do that later. I don't want to make it more complicated than it needs to be right at this moment. But there are ways that people like to rewrite this that make it look different. But let's answer some questions about this. So we can answer, usually 2 types of questions really come up. Either how many bacteria or whatever thing, how many of a thing do I have after so much time? So they're going to give you the time and we're going to find the amount of stuff. Or what time is it when I have so much stuff? So they're going to say, okay, there's going to be 1,000 bacteria, and how long did it take to get to having 1,000 bacteria? So there's 2 kinds of questions. Given y equal to a number, find the time, or the opposite. Given time equal to some number of hours, or whatever the units of time are, right? It could be literally anything. Months, days, years, decades, seconds, hours, minutes, whatever unit of time. Find y. There was one other small thing I wanted to point out here. It's not a huge deal, but I do want you to know that for this exponential growth problem, our, what's the word? Sorry, there's a word I always forget. Just one second. Our growth rate, yeah, sorry. So here, right, our k value is the natural log of 3 over 2. That's our growth rate. And I just want to point out that it is a positive number. The natural log of 3 is approximately 1.1 divided by 2, which is 0.55. You don't need to know this at all, but I just want you to be aware that when we're talking about exponential growth, your growth rate should be positive, right? If something is growing, the growth rate should be positive. We'll see later on when we have exponential decay, the growth rate is actually a negative value. That's why I'm kind of pointing this out now. But here, so for example, we could ask the question, how many bacteria are there after 5 hours? And to my mind, this is usually the easier type of question. If they tell you how much time has passed and you're trying to find how much stuff there is. because for that we can just plug in 5 for t. So the amount of stuff y is going to equal 40 e to the natural log of 3 over 2 times 5. And really, depending on the way the question's asked, we might just leave it like this, right? So if someone said how much stuff is there and we didn't have a calculator, that's kind of our answer. If we did have a calculator, we would actually plug it into the calculator and we would get, so first we would do, how am I going to do? So I would, no, I don't know. I'd probably write it, I guess, as 40 times what this number is. So if I was calculating this, the way I would do it is I would do the natural log of 3, you get about 1.1, and then multiply it by 5, divide it by 2, you get about 2.75, and then I would do e to that. You get 15.58 approximately. It's approximately 40 times 15.58, which then, if I multiply by 40, is going to be approximately 624. Again, you should definitely, when doing the homework, read what they're asking for, right? Most of these questions will probably ask you to give some sort of approximation because, again, while this is a fine answer, I don't know what that is, right? I don't know that 40e to the whatever is approximately 624. And I kind of, right, if I'm saying how many bacteria are there in 5 hours, it kind of makes sense to give an actual numerical answer. So definitely, right, read the question. If it says give a decimal approximation, give one. If it doesn't, you don't have to. Although you might want to anyway, just so you're like, oh yeah, this makes some sense.
Will we ever have to solve like by multiplying e in its decimal form and raise to like ln3 and do all that manually, or?
No.
Okay.
Yeah, and you should probably, I don't think I'm ever asking you to approximate e as 2.7. Like it could come up, but usually we're just leaving e as e and always as e and never as approximately 2.7. The other type of question, which is going to take a little more work to solve, is how long does it take until there are, what's the question I'm asking here? How long does it take for the population to double? So they're definitely asking us how much time it takes to get to a certain population value. So again, we're starting with the model 40 e to the natural log of 3 divided by 2 times t. And now we're asking us how long until it doubles? Well, we have to be careful with this because doubles from when? Well, if they're ever asking you how long it takes something to double or triple or whatever, they're always talking in reference to the initial time. So at the beginning, how many bacteria were there? There were 40. So what we're really asking is how long until there's twice that number. So how long until there are 80? That's how we're asking here. If we started off with 70 though, we'd be like, how long until there's 140? It's always just double whatever you have at the initial time equals 0 moment. So we're given y equals 80, and we're asked to find how long it takes until we get there. And you can see that the thing we're trying to solve for, time, is in the exponent, which means it's going to require some work. So I'm going to start with 80 equal to 40 times e to the natural log of 3 over 2 times t. And almost always, when we're solving for something that's in the exponent, the first step is to get rid of this coefficient. So divide both sides by 40. 80 divided by 40 is 2. 40 divided by 40 is 1, which I'm not going to write because 1 times whatever is just whatever. So I get e to the natural log of 3 over 2 times t. And then to get this variable out of the exponent, we take the natural log of both sides. So the natural log of 2 equals the natural log of e to the natural log of 3 over 2 times t. All right, here's what you're going to see over and over and over again. When you take the natural log of e to some power, you just end up getting that power. So this whole expression here, this is just equal to the natural log of 3 over 2 times t. I can talk more about that in just one sec. But I do want everyone to be, in fact, I'm definitely going to talk about this more in just a sec, but I want everyone to see that when you take the natural log of e to anything, right? If I take, whoop, that was smooth. The natural log of e to any power, it's just equal to whatever that power is. And then we can solve for t. The way I want to solve, instead, I don't really want to divide by this. I'd rather multiply both sides by the reciprocal. So I'm going to multiply both sides by 2 and divide both sides by natural log of 3. All right, I multiplied both sides by 2 over natural log of 3. And that would be a perfectly fine answer. We can also get out a calculator and find a decimal approximation. It's approximately 1.26 hours, which seems reasonable in that we knew it took, sorry, I know I erased it. We knew it took 3 hours. Sorry, we knew it took 2 hours for the population to reach 120. So it should definitely take less than 2 hours for the population to get to 40. Yeah. What time is it? Oh, okay, we're almost out of time. So let me just say, so we'll definitely do more of this tomorrow. I want everyone to follow with me for just 1 second here, right? We know that whenever you take the log with a base the same, so like for example, let me say this. As I take the log base 2 of 2 to the 5th, we could do work. Right? We could say, okay, I'm going to bring the 5 down. This is 5 times log base 2 of 2. Log base 2 of 2 has to be 1 because 2 to the first power equals 2. It's just 5 times 1. But we could have kind of taken a shortcut and said, okay, well, we know that since the base here and the base here are the same, that the answer is just whatever the power is there. Because you're asking 2 raised to what power equals 2 to the 5th. Well, it's the same if you have the natural log of e to the 7th, right? The base here is e. So you're asking, okay, e to what power equals e to the 7th? Well, it's gotta be 7. You can also take the longer path and say, okay, the 7 comes down in front. This is 7 times log base e of e, but log base e of e is 1. So that's equal to 7. It's perfectly fine either way, but we're just going to be doing this so many times that I don't want to have to do this work every time. So I also want to point out, right, if I have like something more complicated looking, like the natural log of, I don't know, e to the natural log of 5 over 6 times t, for example, I don't need to do the work of bringing this down in front. I can just say, oh, the natural log of e to whatever is up here is just equal to whatever is up there. So hopefully everybody is pretty cool with that.